All right, so in this lesson, we're going to continue the discussion of angles in the coordinate plane, but using radians. Now, if you were present in class last week, I discussed what a radian was. I included it in the first part of this lesson, right, in where we did all the coterminal angle stuff in degrees. Now, I'm going to recap that explanation, and then we're going to actually get into doing some problems using radians instead of degrees. Now, the beginning of this lesson is going to mark kind of a turning point in your mathematical careers, right? So similar to how way back, I think beginning of second quarter, I taught you guys imaginary numbers and how that's kind of just a natural expansion of the number system. And it was kind of hard to wrap your head around the idea at first because, I mean, it sounds like it's fake, right, in the name imaginary numbers, but they're not, right? So it's just another part of our number system that we use. What is fake, though, and what is made up are angle measurements in degrees. Now, you guys only know angle measurements using degrees, but really that was made up or invented some years ago. I think I told you guys in class like hundreds of years ago. It's actually more like thousands of years ago. 360 was kind of adopted by the Babylonians, I think, or the Mesopotamia. I don't know. Some ancient civilizations that 360 was a good number to use because it made sense astronomically, right? So we have 365 days in a year. 360 was a good number to use mathematically because it has a lot of factors, right? So if you type in your calculator 360 divided by some number, right? And not like a crazy number, but like if you do 360 divided by 2, 3, 4, 5, 6, not 7, I think 8, 9, 10, and so on, right? So it has a lot of factors, and it was just an easy number to work with mathematically. But really it doesn't make sense in terms of a circle, right? So we know that a circle has a total angle measurement of 360 degrees, right? I'm going to try to draw the best circle that I can for now. Now, we have here, right? So I'm going to take this little piece right here. I'm going to make an angle, right? So we know that this right here is a radius, right? So I'm going to call this R for radius. In class, I did this whole demonstration. I kind of made a big deal about it, but if you take another radius from here to here, and then you have this angle measurement right here, I told you guys this is about, I'm going to say like, it looks like it's about 70 degrees. But let's say you take this radius right here and you fit it so that it's directly on the circle, right? This little arc of a circle, right? So if you remember from geometry, an arc is just is like a little piece of the circumference of the circle, right? So this little piece, I'm going to take this arc right here, and I'm going to say that this is one radius measurement, right? So one radius, I'm going to call it a radian, right? So that's actually what we call it as an angle measurement. So you can see that this about 70 degrees that you see here is the same as if I were to take one radius and wrap it around that part of the circle. All right, so this is a radian measure, right? So this is an angle. Now, if you keep doing that, right, and I did this in class, and you take another radius and you did the same thing, right, you have another radian, right? So I'm going to say that this is 2 radians, and it's as if you took 2 of these approximately 70 degrees and you put one on top of the other. It's probably not even 70 degrees. It's probably more like, I don't know, 50 or so, like that. And if you take another one, and I say that this is another radius measurement, I'm not doing a good job of keeping it to scale, right? But the idea here is that there's another radius that you're wrapping around the circle. I'm going to call this 3 radians. All right. There's a little bit of space left over, right? And this little bit of space left over works out to be 0.14159, and so on, right? And this actually, if you take this entire half circle, right, it gets you pi, right? Because I have 1, 2, and 3, and then I have this little piece right here. This in total, so I'm going to draw this right here. This in total is pi radians, right? Now, before, you guys knew half circle, right? That half circle measurement as 180 degrees, right? So these pi radians actually work out to be exactly 180 degrees. Now, if you keep going and you go all the way around this circle, right? Another pi radians, right? So another pi radians is another 180 degrees, right? That gets you 360 degrees in the circle. Works out to be exactly 2 pi radians, right? And then what else was 2 pi, right? 2 pi you saw in the formula for a circumference of a circle, right? And that's why radian measurements are actually more natural to a circle, right? That's why degrees, were made up, right? They're not really, they don't really have a lot of mathematical significance. What has more mathematical significance is a radian, right? Because we see that an entire circle has 2 pi radians. That's similar to, or no, that's exactly the circumference of a circle with radius 1, right? If I do circumference equals 2 pi r, right, and my radius is 1, right, if I have a radius measurement of 1, that gets us exactly 2 pi, right? And you can see that how this angle measurement relates to the circle, right? So hopefully I could paint the picture well enough for you guys. Let's relate it to what we did in the previous lesson now, right? So I'm going to draw another thing. I'm going to draw another little circle right here. So if I have, let's say, an angle right here, right? This is my initial side. We had said that we can measure angles in degrees on a coordinate plane. We can do the exact same thing in radians, right? So if I go half of, well, not half of a half, a quarter of the circle, right? We said that this was 90 degrees, right? But 90 degrees in radians, well, if half of the circle, I know that if I go all the way around half right here, this is going to be 180 degrees or pi radians, right? Now 90 degrees is just half of 180, so then half of pi is, well, it's just half of pi, right? So 1, or pi over 2, we say. And if I go even further, right, so if I go to this 270 mark, we had said that half of the circle is pi over 2. Well, it's just going to be pi plus pi over 2. That's just going to get you right here, that's going to get you 3 pi over 2. All right, and then if you go all the way around, right, we said that that's 2 pi, right? And then if you didn't start at all, right, it would be just 0, right? So 0 degrees, 0 radians is the same thing. All right, but this is how we can separate our quadrants in radians, right? So our first quadrant is going to be between 0 to pi over 2. Our second quadrant is going to be from pi over 2 to pi, right? Our third quadrant is going to be from pi to 3 pi over 2, and then our fourth quadrant is going to be from 3 pi over 2 to 2 pi, right? And that's going to help when we start applying the previous lesson into this lesson, right? So we're going to start this lesson by finding some coterminal angles, and having a rough idea of where it is going to help us in determining how many rotations to do and in what direction. All right, so exactly like before, to find a coterminal angle, we said in degrees was add or subtract 360. We're going to add or subtract 2 pi, right? Because we have that 2 pi is 360, right? And I Didn't mention that in the previous slide. I think I said 180 is pi, but we have that 2 pi is also 360 degrees, right? So to do a coterminal angle in this lesson is a little bit trickier than before, because a lot of times our answers are going to be expressed to us as fractions, right? Now you guys are going to get calculators for this section, but I can anticipate a lot of you are going to make the mistake of evaluating the actual decimal answer, including the pi. We don't want that. We want the exact answers in terms of pi, right? So for example, if I give you something like pi over 3, right? If I wanted to add 2 pi to that, right, and do a full rotation, keep in mind you can't add these the way they are, and a lot of you are just going to plug this in your calculator, do pi over 3 plus 2 pi, and get some decimal answer, and I don't want that. I want the answer exact in terms of pi. Now to do that, you guys need to be comfortable with converting a whole number to a fraction, right? So this 2 pi is the same as 2 pi over 1, and you want a common denominator, right? I know you guys don't like fractions, but it is what it is for this lesson. You guys need to get comfortable with it. All right, now to get a common denominator, it's multiply the top and the bottom by 3, right? So then we get pi over 3 for the first one, right? That doesn't change. Plus, and then 2 pi times 3, right? Again, I always tell you guys, treat anything that's unfamiliar, treat it like a variable. If it was 2x times 3, right, you would just do 2 times 3, right? So you can do the same thing here. 2 pi times 3 is going to get you 6 pi. And then on the bottom, I have a 1 times 3. And then, once again, treat that pi like a variable, combine like terms. 1 pi, right, there's only 1 pi on top of this one right here, plus 6 pi is going to get you 7 pi, right? And then so 7 pi over 3 would be a coterminal angle, right? That's the idea that you guys need to be comfortable with throughout this lesson and throughout the rest of the lessons, all right? And now we're going to do some examples in the next slide. All right, so here are directions just say find a coterminal angle. It doesn't matter if it's positive or negative, right? Now for this first one, we have 17 pi over 6, right? Now I told you guys you would see a lot of these radian measurements in fraction form, all right? And I don't want the decimal answer. I want the exact answer in terms of pi, all right? Now again, you can add or subtract 2 pi, right? 17 pi over 6 is a fairly big number. Let's see what happens when we subtract. Right, so I'm going to subtract 2 pi, but again, right, 2 pi, I can't combine that with 17 pi over 6 the way it's written, so I'm going to write 2 pi over 1 and get a common denominator, right? So I'm going to multiply the top and the bottom by 6, and then again, like I said in the previous slide, you can treat pi as a variable, right? So 17 pi over 6 doesn't change, and then minus 2 times 6 is going to get you 12. We have 12 pi over 6. And then now that they have the same denominator, I can just go ahead and subtract the tops, right? 17 pi minus 12 pi is going to get us 5 pi over 6. And then there's a coterminal angle. All right. We can do the exact same thing with the next one, right? Negative 4 pi over 3, right? I can add or subtract 2 pi, right? It's already negative, so I'm going to see if I can add 2 pi, right? If I want to add 2 pi, again, I can't do it the way it's written, so I'm going to write 2 pi over 1. And then get a common denominator, right? I'm going to multiply the top and the bottom by 3, and then you get negative 4 pi over 3 plus, and then once again, 2 times 3 is going to get you 6, so 6 pi over 3. And then again, now that they have the same denominator, I know that the bottom is going to be 3, and I can just add negative 4 pi plus 6 pi, right? And that's going to get you 2 pi, positive. All right, this is how I want your answers. I do not want to see any decimals here. All right, now converting from degrees to radians or radians to degrees is just going to depend on what you start with and where you want to end up. Now, theta, we said, is our angle, right? So angle, right? We have our angle here. If we're trying to convert from degrees to radians, if you're starting with the degrees, and then you want to cancel out your degrees, right? 180 is our degree, right? I have that 180 degrees is pi radians, right? So we use a conversion factor, right? And if you're in chemistry or have already taken chemistry, you probably have done some unit conversions with going from grams to moles and moles to grams. That's a similar idea here, right? If you're trying to cancel out degrees, I'm going to want that on the bottom. And if you're trying to cancel out pi, right, a lot of times you see radians in terms of pi. Then I want the pi on the bottom and the degrees on top. All right, so these first three, right, 3, 4, and 5, and 6 are in degrees, right? We can tell that they're in degrees because they have a degree symbol, right? So to convert these to radians, right, I'm going to want degrees on the bottom. So I'm going to say times 180 degrees on the bottom and then pi radians on top, right? And then I have that the degrees are going to cancel out. And then really I just want to simplify 135 pi over 180, right? I don't want to leave my answer like this because it can definitely be simplified. And if you simplify this, right, you'll get 3 pi over 4, right? Simplifies a lot. And then that's your answer in radians. All right, we can do the exact same thing with the next one, right? Because it's in degrees, and I can tell it's in degrees because I see the symbol, then I would multiply by pi over 180, right? Because 180 was in degrees. I want to cancel out my degrees, and then you're left with 540 pi over 180. And then again, you can simplify this a little more, and you're going to end up with 3 pi. All right, and there's your answer in radians. Exact same thing with number 5, right? 45 degrees, I'm going to multiply it by pi over 180, right? I'm going to want my degrees on the bottom. That's what you're trying to cancel out. All right, cancel out your degrees, and then you end up with 45 pi over 180, right? And then upon simplifying this all the way, we end up with pi over 4 in radians, right? So hopefully you see not too difficult. You guys do have calculators, right? So it shouldn't be an issue. And then times, again, this is in degrees, pi over 180. And then, again, degrees cancel out, so we get 90 pi over 180, and this gets us pi over 2. All right. Now, before I do 7, 8, and 9, I want to really quickly do 10 and 11. Notice that 10 and 11, I don't see any sort of pi, but I also don't see a degree. If you don't see a degree symbol, assume it's in radians, right? That's why maybe last year in geometry, depending on your geometry experience, your teacher might have been really picky with if you have the degree symbol there or not. That's because when you're talking about angles, if you don't have a degree symbol, we assume it's in radians, right? So you need to be careful that if your answer is in degrees, write the degree symbol. Otherwise, let's say it's on a test or a quiz, you will lose points for that. And if it's in radians and you for some reason put a degree symbol there, right? So something like that, you put 5 degrees when it's 5 radians, that's also wrong, right? So just be careful with that. So now I said I would do 10 and 11 before doing 7, 8, and 9, right? So I'll do that. If this is in radians, then I'm going to multiply this now by 180 over pi, right? I want my degrees on top, right? So then 5 times 180 is going to get you, I think that's 900 over pi, right? Degrees, right? And this is something that I would simplify a little bit, just because degrees, we like the exact number answer, right? Number or decimal, usually we don't use a lot of decimal places with degrees, right? This is going to get you about, if you plug it into your calculator, about 286.5 degrees. All right, and then same thing with 11, right? So I have times 180 degrees over pi, right? Just because, again, I don't see a degree symbol, so I assume it's in radians, and I want degrees on top if I'm going from radians to degrees, right? And so if you do this, this is going to get you, you just multiply 2 times 180 is going to get you 360 degrees over pi, right? And that's going to get you about 114.6 degrees. Right, and there's your answer in degrees. All right, I'll circle this one too. All right, and then now 7, 8, and 9 are going to work out pretty nicely just because we have a pi in there already, and it's going to cancel out, and you'll get a nice whole number. All right, so this one right here, 5 pi over 6, right, I can do times 180 degrees over pi, right? And because pi cancels, right, we get a nice whole number now, right? So 5 times 180 is going to get us 900 degrees over 6, right? And that's going to get you 150 degrees. All right, and we could do the same thing with 3 pi over 4, right? So times 180 degrees over pi. Cancel out your pi's. And then you could even also cross cancel, right? If you don't want to multiply straight across. So if you cross cancel, 180 and 4 are going to simplify, and then 180 is going to become 45 degrees. And then if you do 45 degrees times 3, that's going to get you 135 degrees. All right. And then lastly, number 9, right? Negative pi over 2. I just want to do the exact same thing, right? So times 180 degrees over pi. All right, and then pi and pi are going to cancel again. And then 180 divided by 2 is going to get you 90, right? So we get negative 90 degrees as our angle here. All right, our last major topic in this lesson is going to be arc length and sector area. Now, you guys have done this before in geometry last year, but you did it in a little bit of a different way just because you didn't know what a radian was, right? But here with a radian measure, right, it actually makes it a little bit easier, right? So arc length, right, we call that S, right? So that in the very first slide where I started writing stuff, and I was describing that I gave you that whole spiel on what a radian is. There was a formula there that I kind of glanced over, right? Because it was going to show up again, right? And it's going to be this S equals R theta, right? Or theta R, right? It doesn't really matter. And this is going to be the area of, the formula for the arc length, right? S is going to be your arc length, R is going to be your radius, theta is going to be your angle, right? This is super, super important right here. Your area must, your angle must be in radians, right? If it is not in radians and it's in degrees, you will get the wrong answer. So you need to be super careful with that. But yeah, this is the arc length formula and the area formula. It looks kind of strange right here. I'll write it out a little bit better. It's going to be 1/2 r squared theta. All right. And once again, this theta, your angle must be in radians. And we're going to do some examples and then we'll wrap up. All right. So we're given a circle with a radius of 18.2 centimeters, and I want to find the arc length and the area of the sector where theta is 3 pi over 8. Right. Now 3 pi over 8 is already in radians. It looks kind of like the same as what we've been doing, right, with our pi measurements, right? But you also don't see a degree symbol, right? That's the biggest thing that's going to give it away. You don't see a degree symbol, so you know for sure that it is in radians. All right, so I'm going to label everything that we have. We have a radius of 18.2, right? That's our measurement. That's the number, right? I know it has a unit there, but we'll put the unit at the end. And I have a theta is 3 pi over 8, right? I want to find S. I don't have S, and I also don't have the sector area. I'll start with the arc length. I know that S is going to be r theta, so I know that my arc length is going to be 18.2 times 3 pi over 8. All right, so then I'm going to get that this is 18.2 times 3 should get you about 54.6 over 8. Now this is the exact measurement in centimeters, but to get a decimal approximation, this was going to get us about 21.4 centimeters. All right, something like that. And then you can do the exact same thing with area, just use the respective formula. So my sector area is going to be 1/2 r squared theta. All right, so my sector area is going to be 1/2 18.2 squared times 3 pi over 8. All right, now, I wouldn't try to waste any time trying to write out the entire thing, right? Just because there's a lot of things going on here. Just make sure you're doing order of operations, and you do this 18.2 squared first, and then you multiply it by a half, and then you multiply it by 3 pi over 8, right? But if you plug this correctly into your calculator, you should get that this is about 195.1 square centimeters, right? Remember the units here, since it's an area, are going to be in square units, right? So it's going to be something like that. All right, we're going to try the same thing. This time, the only difference is that we're given an angle in degrees. Now, remember, if it's in degrees, you don't want that. You need to convert it to radians, right? So it's going to be 144 degrees, and then the conversion was pi over 180. All right, and then that's going to get you 4 pi over 5. All right, so that's the only difference, right? We still have the same radius of 18.2 centimeters. All right, and then to find the sector, I mean, not the sector, I keep saying sector because it's S, but the arc length, it's going to be 18.2 times 4 pi over 5. All right, now if you put this into your calculator, then you should get that this is about 45.7 centimeters. All right, and you can do the same thing with area, right? Plug it into that formula. This is going to be 1/2 18.2 squared, and then times 4 pi over 5. Right, once again, I wouldn't try to simplify this any further, right? This is just going to get you, if you plug it correctly in your calculator, doing order of operations is going to get you 416.2 square centimeters. All right, and that's all the material for this lesson, right? So hopefully you guys are a little bit more comfortable working with radians, right? Converting from degrees to radians and vice versa, and hopefully you see how it's kind of similar to what we did in the previous lesson in degrees.